All right, pass it up to the empty desk next to Mark. Who's not here? Oh, any more purple sheets? Oh, yay, thank you. Purple sheets.
Mark out the ones we're gonna do.
Yeah, but she said you guys could mark out, but then that's like not your official change until schedule change time. Any more purple sheets? Okay, reading guide 13 here, and let's do. Ooh, Drax is going to practice. All right, we're not gonna work on this sheet. I'll wait on you guys. Don't be rude. We're going to be working on phase diagrams and heat curves today. This is all about the states of matter today. But we're specifically really talking about solids and liquids and a little bit of gases today. Because after today's talk, we're going to talk about gases exclusively for like the next 5 days. Because gases have a lot of interesting properties and some different variables that we'll talk about. That's not happening. Okay. No. So today we're going to kind of hit all the phases of matter. I'll give them a second when they come back. And after that, we'll be focusing mainly on gases, okay? So this is going to be quick and easy chapter 13. All right, and I think a lot of it will be very familiar to you. So just kind of ask me questions as you need to, because I want to make sure that you're getting all the help you need. I'll put some more water in this in a second. Okay, so from review, way back, what does STP mean? Standard temperature and pressure. Standard temperature is, what's the number? Well, 25 degrees Celsius? No, it's 273. It's 0 degrees Celsius, which is 273 Kelvin. Those two things are equivalent. 0 degrees Celsius, 273 Kelvin. Standard pressure, how many? What? 1 atmosphere, right. Did you guys see in your reading a little bit, or and if you didn't, write this down now. 1 atmosphere is equivalent to 760 millimeters of mercury, mmHg, millimeters of mercury, which is equal to 101.3 kilopascals. Kilopascals is kilo, like, you know, a metric unit, or a prefix, and pascals is just a guy's name. Okay, so millimeters of mercury is literally standing up on end, measuring out in like millimeters, not centimeters, but millimeters, a column of mercury liquid. So these are all equivalent. Just like I can say 1 foot is 12 inches, these will serve as conversion factors for us when we need them to. So, for example, let's look at this one down here. Oh, I forgot what torr. 760 torr. 760 and 760 repeat themselves, so millimeters of mercury and torr are the same. Okay, so if I wanted you to convert, this is just a quick review because we eventually will be doing more of these. If I wanted you to convert 700 torr to atmospheres, basically the two quantities given to you above that matter is this one and this one. So those two, I pop it down in a fraction. What goes on top? 1 atm, one atmosphere over 760 torr. All right, so then that's going to allow me to, I can already kind of guesstimate it's going to be less than 1 atmosphere. Maybe like 0.9, 0.8, something like that. That number is, don't have it written down right now. 700 divided by 760. Oh, this, what is it? I want an exact one, that's what I'm going for here on this one. Okay, so 0.92 atmospheres. Cool. Okay, so that's just an easy conversion. We'll be working with those for the next couple of days. All right, so I just want to go ahead and tell you up front, this is something that we will be referring to a lot. Okay, so the states of matter, what are they? Solid, liquid, gas, right? So we already know a lot about solids, liquids, and gases. Solids, liquid, gases, plasma. Who's ever been to, I'm guessing, I don't know if it's still Spencer's, the plasma ball? Put your hand on it. Plasma ball. Yeah, the plasma ball. So lightning, and so whenever lightning goes in the sky, it's actually interacting with gaseous ions. Gaseous ions are not gases. gaseous ions are different than just straight up gases. So they act a little differently in terms of their phases of matter. So that's why there's actually 4 states of matter, but we know a lot more about these 3, less about the plasma. Aurora borealis, you know what I'm talking about? That's plasma, which is cool. So plasma is like the coolest state of matter. It's actually the hottest state of matter because ice is the cool, or the solid is the coolest. Thanks, guys. Okay. So we're going to talk today about how we can transition between all the states of matter. So you knew solid to liquid is melting, liquid to gas is vaporizing or evaporation, and then backwards condensation and freezing. Those are all very familiar. We might talk about ionization today. We'll see. Okay, this is on your paper. I am asking for you to abbreviate these 2 columns on your paper. I'll be quiet and let you do that a little bit, and I'll kind of conclude with you on that. I'll scroll down. I'm working on it. All right, I'll come right back down here because there's a couple things on this chart that are very important, like the axes over here are kind of labeled. So the solid to liquid to gas, we have differences in the arrangement of the particles. So the particles have a definite shape and volume here. So if it's like, you know, it might be a little cube. So it'll be like 1 foot by 1 foot by 1 foot or so forth, right? So very tightly, sorry, say some 0. Very tightly packed. Very tightly packed means that they have very little space between them, right? Then as you go to liquid phase, they are starting to move apart some, but they're still in this general volume. So they have a set volume, but no set shape, right? So that's how the liquids and solids are slightly different from one another. In terms of their motion, all particles, even your body right now, have energy. Therefore, they have energy of motion. They're vibrating. So they have vibrational energy, which means that your whole body is shaking right now, right? And even like our food, right, we have, the food we eat has a little energy in it, right? So chicken, or let's say, what do you put in the microwave? Ramen. Okay, water and ramen. Put it together, you're gonna put it in the microwave, right? The way the microwave works is, how? Anybody? What kind of waves? Microwaves, which are just straight up energy, right? Microwaves go into the water molecules and pretty much increase their kinetic energy until it feels really hot. Okay, so basically the water molecules are kind of vibrating. The microwaves go in and energize the water molecules. It shakes them, so they're like violently vibrating. And when you violently vibrate, you increase your kinetic energy, which kinetic energy is essentially temperature increase as well. So if you put yourself in a microwave, most of your body is made up of what? Water. Your body would increase in the kinetic energy. All the water molecules in your body would be shaking violently, and you would essentially explode. Okay? They have these microwave, they're not microwaves like you put your food in that, but they have different microwaves that it's like it's a free beam of microwaves that come across like this little opening at UNC Charlotte, and you have to be very, very careful when you use it, because if you put your hand in there, you will like demolish, like a finger will pop off or something. So, microwaves are some serious business, but basically, they increase the vibration. So, liquid, the particles can flow, okay? So we know that they can flow. They actually will take the shape of their container. And then comparing liquids and gases, they get more loosely packed, so they don't have any set shape, or they don't really have a set volume either, because they have some expansion, they have some ability to expand, and they have constant random motions, okay? Extremely energetic. Okay, so I've spoken of energy this whole time. I don't know if you saw this on the side, so write this now, but kinetic energy increases as you go from solid liquid to gas. So draw an arrow, put KE, kinetic energy, increases as you go from solid liquid to gas. And with that, as the kinetic energy increases, the molecules are vibrating a lot more. That means molecule 1 and molecule 2, they can't interact as much because they're just so energetic. So increasing kinetic energy down these phases correlates with there's weaker attractive forces as you go from solid liquid to gas as well. Does that make sense? Just because they're just so energetic, the two particles that are now gas have no attraction to one another. They're far apart. All right, so then this last column here. All right, increasing temperature. Increasing temperature. Just a little bit of increase in temperature will pretty much cause no change on a solid. Okay, they vibrate a little bit more, but nothing crazy is going to change. I mean, if you heat it up enough, the solids are going to melt. It's going to melt, but we're not talking about huge temperature changes. Increasing the pressure, no change. Okay. I will say up here in parentheses for increasing temperature, there could be some thermal expansion. Basically, it's like if you ever worked with like an automotive engine or something, when it's really hot, if you try to like take it apart or something, the bolts and the screws, they will not come out, because all the metals in there expand just a tiny bit when they get that hot, so they're stuck essentially in the holes. But if you let it cool down, they kind of have some thermal condensation, and they shrink down a little bit. So with temperature, there could be a slight change. Okay, liquid, again, increasing pressure will do pretty much no change. It could compress very, very little, because there is a little bit of space between the liquid molecules, so you can smush them together just a tiny bit more. So it depends on how much pressure we're talking about here. There's compression that is a possibility. Increasing temperature essentially will cause little to no change, and I'm going to put TE again, TE, thermal expansion. That also can occur. Just a little bit, because the liquid particles are getting more excited. Okay, so here's the big dog. Gases. One thing I didn't write over here, I wrote flow for the liquids. Gases can flow as well, and I'll show you an example of that in a second. They can flow, meaning they can like kind of move together as a unit. What's up? Yeah, TE, thermal expansion. Okay, so gases, increasing the pressure. Okay, here's what I need you to do. Drop your pencil. Give me a box of air. Make a little box of air. You got it? Got it? Okay, everybody's got one, all right? Everybody's got their own. Put some pressure on that box of air. What did you just do to that air?
Compress.
You compressed it. What did you do to the volume of it then? Huh? The volume was here. I had a big box of air. I increased pressure on it. Okay, so this air I have here has lots of space between the particles. I can smush them together. I feel it. They're smushing together. So increasing the pressure causes a change in volume. Okay, so that's actually decreasing the volume quite a bit. Yeah? Okay. So in the second case, increasing temperature. Now, got your box of air. Heat that baby up. What are the particles doing in there now? They're shaking violently and expanding, okay? Because as they shake violently, they're going to end up expanding. So in this case, increasing temperature will expand the volume, aka just change the volume. So what you're seeing here is that the condensed matter, like solids and liquids, they're fairly well condensed. Pressure and temperature changes don't really influence that, period. Gases are very, very different. They're very spread out. So if you increase the pressure, decrease the pressure, increase the temperature, decrease the temperature, it's going to cause vast changes. So that's the most important part from this little chart here. But I thought the chart was pretty good summary of everything here. Okay. So whenever, actually I'll come to this in a second when we go to phase changes. Okay. So here's essentially what this looks like. This little like curve here just means little energy, a little bit more energy, a little bit more energy. Work with me here. Work with me here. So as you add energy, you're going from what state, to what state? Solid, liquid, gas, right? Adding energy. What was the term I used for adding energy in a reaction? Endothermic, right. So what I'm saying is this is an endothermic state change or phase change as you go from solid, liquid to gas. And then if you go backwards from gas, liquid to solid, what's happening to the amount of energy as you go back? Exothermic, right. It's releasing extra energy because it's going from high energy to low energy states. So that's what this right here is. Okay, so write down what you need to here. I'll be quiet and I'll explain. This is important. We're going to see this on a phase diagram in a second. You would probably put in the back of that, but I'll so I just printed out like graphs and charts on that. I'll show you. No, it's hard. Huh? No, so we could eat it. Oh. Give it the program. Moon. So we know normally at room temperature water exists as a liquid. We know when we increase the temperature of water, it goes to gaseous state. We know when we decrease the temperature of water, it'll go to solid state. So we have the power and capability to change pressure and temperature. And if we do that, we can actually change the state of matter. We have these closed conditions, we can do that. So we can change the state of matter of any substance point, period. And we're going to see that on some phase diagrams in a little bit. Or we can change the state of matter simply by just changing temperature, aka adding and decreasing amount of energy in a substance. So this is kind of just the intro at the top here. This is the part that I need you to definitely write. Melting and freezing, the word for melting, another word for melting is called fusion. So we're going to hear fusion in just a minute as we go through some examples. So this is some general substance. I'm calling it X. If X is a solid and I go to liquid, tell me, does solid have low, medium, or high kinetic energy? Huh? Low kinetic energy. Okay. So solids have low kinetic energy. Well, I'm going to liquid, which has medium or higher, right, kinetic energy. So did energy go into that substance or come out of it? Into. Energy is in, so it's delta H is positive or negative? If energy goes in, I'm adding it to it, right? Adding the energy is a positive. That's endothermic, right? So if you just told me that when from low to high kinetic energy went in, well, that's endothermic. So I think you could get there. But don't forget, endothermic is a positive delta H. So this physical process is an endothermic process. Okay, so going the same thing from liquid to solid. Liquids are medium kinetic energy. Solids are higher, right? High kinetic energy. So again, what kind of process do we have? Oh, I'm sorry. I was thinking I was doing gases, my bad. To low kinetic energy. So we're going, what type of process in terms of endo or exo? Exothermic, because it's losing energy. Losing energy is an exothermic process, so delta H is negative. So you should be able to tell about phase changes with their endothermic phase changes or exothermic phase changes. Okay, so this bottom piece here is referring to this delta H we just mentioned, and we call it something very special. the process of melting. Notice this first example, going from solid to liquid. This is melting. What's the second process? Freezing, right? So this is no news to you. Okay, so we're freezing. So these two are actually exactly opposites of one another, but their signs are different. So what you would think to yourself is, okay, I'm going from solid to liquid and then liquid back to solid. The number, so like this is my, I don't know, this is like, oh, I do know this number. 6.01. Delta H for this is 6.01 kilojoules per mole. Okay, this delta H is either positive or negative based on which phase of matter is changing. So that's called, this delta H has a name. It's called the enthalpy. Enthalpy is a word we know of fusion, meaning melting. And so that is literally what I have. I have it written in unit form up here in blue. The amount of heat, aka kilojoules, energy, needed to melt or freeze, depending on which phase we're changing to, 1 mole of a substance. So what I've written is kilojoules per mole, 1 mole in this case, and that is the enthalpy of fusion. So it's just combining a couple of our concepts here. I just want you to know fusion means melting. So for water, it is. It's different for other substances. So I'm just talking about water because we're all really familiar with that. It's just a number I would always tell you. Like, I don't expect you to know that number. All right, give you one more second there. Then we're going to do the next states of matter changes. So my goal is we'll finish notes, do a little bit of practice, and then we have an inquiry lab activity, which will be fun. We'll see if we get there, guys. Okay. So you tell me here, okay? Write down what you need to and shout out exactly what we did earlier, but for this new phase change. What are we writing here? Huh? Low? I mean medium? Medium kinetic energy? High kinetic energy. Huh? Yes, it's endothermic because you're putting energy into the process. Delta H is positive. And what process is this from liquid to gas? Yep, you can say evaporation or you can say vaporization. And then the next one, high kinetic energy down to medium kinetic energy. And that process is exothermic. Therefore, delta H is negative. All right, so based on what you have in terms of your enthalpy of fusion information, tell me. I have it at the bottom. I'm going to wait to show you this. This is delta H of vaporization. I call it HVAP. Okay? Delta H of vaporization is the energy to what? To vaporize, okay. How much? 1 mole of liquid, good. Or I'm going to say liquid or gas, because I can say vaporize or condense. Oh yeah, sorry. I didn't write condensation down here. This process is condensation. Going from gas to liquid. So these delta H's, they just have names, that's all. But the names are very helpful, because if I say delta H of freezing, guess what? You already know the process is going from liquid to solid. If I say delta H of vaporization, then you're going to say vaporization is liquid to gas. I could even call this, if I was talking about the condensation one, I could call this delta H of condensation. And that would help me know Oh, I'm talking about the exothermic version of that versus the endothermic version of that. They're the same exact number. So the important part was delta H is the same magnitude in number, but what about their signs? What about their signs between these two processes? Right, they're opposite in signs. So they're one's positive endothermic, one's exothermic, so negative. So delta H for either of these processes are opposite of one another, have opposite signs, same magnitude. All right, so let's look at some definitional stuff about boiling versus evaporation, because this is a big misconception. If you are at home trying to boil some spaghetti, some water, don't boil spaghetti, boil the water. That'll be gross spaghetti. Ew, I'm just thinking about bubbly spaghetti. Okay. So if you want to boil the water, where are you putting? Where's the heat source at? Your stove. So in your little boiling pot of water, where's it starting? The bottom. So you're heating from the bottom, and it's matriculating up. So that way you have hot water at the bottom, hot water at the middle area, and hot water at the top. And soon it'll start to boil, right? So boiling is a process that happens throughout a liquid, all the way through the column of water you have. The process of evaporation, only that word, evaporation, is only talking about the liquid molecules that are going to gaseous phase at the surface at the top of your column of water or whatever, okay? You can't evaporate something in the middle of a big column of water. Where's it going to go? Right? There's no place for it to go. So that's the only difference really between evaporation and boiling. And we just wrote down enthalpy of vaporization up here in green. I don't know where it went. Right there. We just wrote that down up top. Thumbs up when you're ready. Thanks, dears. All right, so far, somewhat familiar, like states of matter, phase changes, kinetic energy is probably the biggest new thing that we're focusing on right now. Okie dokie. So, I don't want to do this right now. We'll do that. All right, so this one's just our new version, two different phase changes. You can write this down or not. But sublimation. What is the process of sublimation? Straight, actually, sublimation is opposite that one. That one's solid, straight to gas. Okay, so sublimation is simply going from a low kinetic energy solid to a high kinetic energy gas, endo or exo process. Endothermic, we're going from low to high. So we're putting energy in, so the delta H is positive. Adding energy means positive. And then a good example of sublimation is dry ice. And I'll go get some from the back right now. We can write that down. My dry ice, I just accidentally froze the water around it, but not the lining like I want to. So I add a little bit more. Here to be 18 bucks. I can't remember. I don't know. Oh, they did ask me ID for some reason. This was writing at like 6 o'clock in the morning. And like, who's this dear lady? You can't touch your hands because it's extremely cold. You guys see it? You see the timing? It's solid phase right now. So the water molecule, or you hear it, that's it screaming because it's making gas and scooching it across the surface. Because it's extremely cold. Because it will burn, it will like cause a frostbite in your hand. So you don't. And so it's freezing the bottom of this glass right now. But I told you I'd show you how this would flow. Feel a little nice. Okay. It's just gas. I'll put it on the back row. I accidentally poured water on one person last year because there's water in here. I didn't mean to. I just didn't know where it was. It's so foggy. This is how they make fake fog. You know? So there's water in there. Now Troy doesn't know what. So, anyway. Alright, so this will chill here for us. Entertain you. Alright, deposition is our last one. Josh, turn around, boy. Alright, deposition is our last one. And this is one where you go straight from gas to solid. So, endo or exo? Exo, you're releasing that extra energy. Right, so you're releasing that extra energy. A good example of this is an air freshener. You've heard, or you've seen like those like waxy looking air fresheners, and you put them out, and eventually they disappear. It's because they're depositioning. No, I lied to you. Sorry, this one air freshener is the sublimation one. Air freshener. That's the one that's in solid gas because it's refreshing your home. And then a good example of deposition is frost on the ground, where you have, at the end of the or in the morning, the liquid part or the gaseous particles in the air have settled on like plants and stuff, which is frost. Okay, so now let's look at this guy. Have you seen one of these before? Phase diagram. That copy is a little weak on your paper, so that's why I have this again. So I have this bigger on the next page. Okay, so this is called a phase diagram. If you would like to sketch yourself one, because that one's kind of dark, basically what you're doing is you have an axis. It's labeled pressure and then temperature. And I'll scroll down to the bottom so you can see it's temperature on the bottom. So it's pressure versus temperature. And it always is arranged in this way. There is kind of a Y shape in the middle. And it is in order of states of matter. Solid, liquid, gas. It's always arranged in that pattern. So the phase diagrams are very, very specific to one compound. Okay, so I have to make a new graph for every single compound: water versus carbon dioxide versus oxygen versus helium versus whatever. I have to make a different phase diagram. But they're very helpful because they will let you see at what point, what temperature a phase change will occur at different pressures. So we live at what atmospheres of pressure? We live at 760 millimeters of mercury, which is one atmosphere. One atmosphere, right? So we live at this little place right here, okay? Note to self, when I say normal pressure, normal, the word normal means the normal one that we live at, which is one atmosphere. So normal is one atmosphere. You have to know what normal means when I say normal. So this is a phase diagram for water. Yeah, this is for water. So if I cross this line, what phase change is happening? What phase change is that? What's it called? Melting, right. And if I go from liquid to gas here, it's evaporation, right? Vaporization. Okay. So at normal atmospheric pressure, when does that happen? What you do is you basically look at your one, you scroll your finger over until you get to the line between the liquid and the solid and the liquid, and then you drop it to the bottom of the graph. Drop it to the bottom of the graph to see what temperature that is. So what is this telling you? This is just a graphical way to say what we need to know, right? So you're seeing that at that right there, that point is when you're going from solid to liquid. So that's melting, and the temperature at which this substance melts is 1 degree Celsius, which is water's melting point. This is very familiar to you because it's water, but I can give you anything else and you just have to read the graph. So if I want you to tell me where water boils, aka the vaporization here, then you would scoot your little finger over to the liquid to gas transition. See, that's at the 1 atmosphere mark. Drop it down to see that it boils at 100 degrees Celsius. So this is a valuable tool when you have an unknown substance or something like that. Now, what if I upped our pressure? Let's say I wanted you to tell me, are we on top of a mountain or are we under the ocean if I say we're at 2 atmospheres?
The ocean.
Under the ocean, okay? Atmospheric pressure is basically the amount of air sitting on top of you. So if you're on top of a mountain, do you have less or more air sitting on top of you? Less, because you're higher up in the atmosphere. So there's less pressure pushing down you. So you might be at like 0.5 atmospheres on top of Mount Everest. But under the ocean, you're sitting on lots of air and all this water on top of you. So you have a lot of pressure sitting on top of you. So at 2 atmospheres, when does this thing melt? Well, approximately the same because that's a straight line. But when does it boil? Drop that down there. And you can see, we don't have any numbers here, but you could say maybe it's like 125 or something like that. So it's increasing in terms of its boiling point at higher pressures. But below the ocean, so like, below 0.5 atmospheres on top of a mountain would have a different melting point. I'm sorry, is that melting? Is it?
No.
What's this phase? What's this phase? So what's that point? Sublimation point. Yeah, so it would sublime at, whatever, negative 10 degrees Celsius here. And it has no boiling point because it's already to gaseous state. So it's different based on where you are on the ground. Are we okay with this phase diagram? Yeah. This is just a point telling you what that point was. Don't worry about the numbers here. I'm going to do another practice with you. Hold on, okay? I'm going to give you a practice. This is the practice one, okay? You guys have this one on your thing you do someplace, but it's hard to see, so I have it up here as well. So now we already know normal atmospheric pressure is 1 atmosphere. We know that. As we go, it says what happens to the particles from temperature 100 to 0 degrees Celsius. So as we go from 100 to 0 degrees Celsius at 1 atmosphere, that means we are at this. Why does it say 101.3? What was that number earlier? That wasn't the torr number. That was the, which one? kPa, kilopascals, right. So this is 1 atmosphere. Don't forget, it's equivalent to 101.3 kilopascals. So that's actually still 1 atmosphere of pressure, okay? So as we go from 100 degrees all the way back down to 0 degrees, we're basically going from gas to liquid to solid. We're just going the opposite direction. Okay, so we're going to, is it this one? Yeah. So on your, did I type out these on your paper? Yeah? Okay. So let's look at segments B through C, and we need to know what this represents. So answer these questions with me. So I'm going to point where B and C is on the graph because it's hard to see. So B, I'm going blue here. I may have just covered this up. Where's B? Oh, here's B. B is the triple point, okay, up to C, which is this point up here. What is this line separating? Solid and liquid. Okay, so at this point, this is the exact point where what process will occur? Melting or freezing, right, depending on which way we're going with it. So this is called the physical equilibrium between solid and liquid. That's just like the phrase you say to represent this line. And it's also called the melting point or freezing point, if we're talking about a specific point along that line. And so physical equilibrium is basically, like I was showing you on the warm-up, solid is going to liquid, but liquid could be going back to solid at the same time. So there's a double-headed arrow representing that they're going back and forth and back and forth and back and forth. If you push them past the point, they'll turn totally to solid. If you push them past the point, they'll turn all the way to liquid. It depends on the temperatures. Okay, so then what's A to B represent? So A to B. B is still down here at the triple point. A is over here. So what does this line represent? So sublimation, because it's going from solid straight to gas. So it's tell me what I wrote previously. Okay, between solid and gas, aka the sublimation point or deposition point. Good. I'm just abbreviating here. And so the physical equilibrium is between solid and gas and back. Okay, B to D. B is still down here at the triple point. D is up here. This is D. Okay, so what does this one represent? Liquid to gas, which is, so the physical equilibrium between liquid and gas. What is it? Oh, so I'm going to put boiling point, because boiling point and vaporization point for that point is going to be the same. Or condensation point, because you're going backwards. So that's the equilibrium between liquid and gas and back. And yeah, let's skip number 4, let's do number 5. It's frozen all the water in here. Alright, so on our graph we need to look at the slope between the solid and liquid, and let's look at the slope and let's figure out what does this mean for pressure. So what's the melting point of the substance as pressure increases? So looking at this, we know the melting point is this one right here. As you increase pressure, what's happening to the temperature of the melting point? It's decreasing, right? So you can see, like, at this pressure, the melting point is whatever this is in Celsius, like almost 0 degrees Celsius. Over here, it's definitely 0 degrees Celsius. Right here, it's less than 0 degrees Celsius because the slant is a negative slope. So basically, the negative slope means as you increase pressure, the melting point temperature decreases because it's a negative slope. So if I like smush ice, okay, ice being, liquid water, if I smush ice and I push it, I can actually melt ice I would have to melt ice at like -4 degrees C or something like that versus at 0 degrees C under really high pressure conditions. Normally, it melts at 0 degrees Celsius, right? It starts to melt there. But if it's under high pressure conditions, it's going to melt at like -4. So I'd have to decrease the temperature even more. So that's abnormal. Water is pretty much the only thing that has a negative slope. Yeah.
Is that why I like ocean salt?
Basically, and there's a lot of salt in there. It's called a colligative property. If there's a lot of salt, it disrupts the ice formation ability. Okay, so this is abnormal, very abnormal to have that slope. So the pressure, we just answered that. So number 6. What happens to the boiling point as the pressure increases? Boiling point's between what two phases? Liquid and gas. So here, what happens on the liquid to gas? As you increase the pressure again, what's happening to the temperature at which it boils? Increases, right. Okay. So, Chris, will you be my water? Okay. You're going to be, no, I want you to be my atmosphere. Okay, stand up for me, man. Stand up. So, I am the water, and he is the atmosphere. We're going to play hide and seek. Come over here. All right, so he's the atmosphere. Look, raining down on us, okay? So he's a really strong atmosphere. Water has to basically, the water vapor that's forming and boiling has to eventually just push up and push up and push up and push past the boiling, or push past the atmospheric pressure. Okay, but if the atmospheric pressure is strong and I'm just, barely not hot enough and the boiling is not occurring, it's not going to push past it. Therefore, the water will not turn to gas and it will not boil. Okay? So, at higher pressures, he's really, really strong. I'm going to have to really get some energy here to boil because I cannot go past the dang atmosphere. I would have to push way high to get, or heat up a lot to get the pressure to overcome the atmosphere. Thank you. Thank you. So that's why the pressure increases, the temperature increases here. Okay. Thank you. Notice what's different. Look at these two graphs. Yeah, because she just has to because she has to. Okay. Actually, you can see right here, positive slope. This is a negative slope, so this one's water. This one is different. This is carbon dioxide. Carbon dioxide has a totally different graph and everything. So I'm not going to go through that right now. Okay. Let's do, this will stand, give yourself a stretch break real fast. A minute stretch break, and then I have this last two examples. And we'll move on. Go see somebody, high five somebody. be gas and atmospheric pressure with somebody. Almost done. Give me like 5 or 6 minutes, okay? Bye, Jamie. Okay, come back to me. I need you for about like 5 to maybe 10 more minutes max, okay? So, what was the Y one called? What was the name of that chart? Phase diagram. The one with the pressure on the y-axis and the temperature on the x-axis. That's called a phase diagram because it's got all the phases of matter, right? This right here, I know it doesn't look like it. It's called a heat curve. Do you see the curve? No, me neither. It's called a heat curve, people. Don't know why. It's a heat stair step, but it's called a heat curve. So if I say heat curve, this is what I'm talking about. I just wanted to go ahead and put that up front because the other one has curves, right? It's got the little Y with the curves. That's called a phase diagram. This one's called a heat curve. Two different, totally different graphs. This graph has temperature on the y-axis and time, or sometimes it's called heat added on the x-axis. So you guys have this on your paper as well. Just make sure you point that out to yourself. Okay, so yet again, it's talking about the phases of matter because we all know as you increase the temperature of a phase of matter, it goes from solid to liquid to gas. So you can see it's solid on this slant, liquid on this slant, and gas on this slant. So what's happening here? The phase change, right? So the phase change is happening on the plateaus, on the flat spots. So this is the first phase change. This is the second phase change. So what phase changes between solid and liquid? Melting. We know this. Okay, so this one's the melting one. And this one over here is the boiling or vaporization, whatever you want to call it, one. All right, so every single point matters here. Every dot, every transition right here. So as you see, there's a little corner. This corner that you pass, that right there is the very, very, very first point of when melting will occur, right? And then as you continue, this is the first point at which boiling will occur. So those you can read off the temperature, depending upon what the substance is, you can read off the boiling temperature and the melting temperature really easily. So now we need to talk about what's truly happening to the molecules on each of these phases. So what's the first thing you notice about what's happening on that plateau? Or what do you notice is not happening? What's not changing? Huh? Temperature, okay? So what we're saying is, when something is melting, the temperature of it's not changing. Does that make sense? No. Most of the time you're like, oh, it's melting, it's hot, it's getting hot, right? No. Right as the solid that you're trying to melt, the solid will slowly creep up in temperature, and then it'll go to a point where it transitions its molecules, but the temperature of the solid is no longer changing. Once it reaches fully melted, and it's all liquid at this point, that's when the temperature is going to creep up again, to the point where it just can't be a liquid anymore. It's going to be so hot and energetic, it starts to phase change. And at that point, the molecules are moving around, changing up their molecular arrangements, until they get to the point where they can no longer stay in a kind of liquid phase and get to be evaporated. Yeah.
When you have a metal and you're at melting, you put it to melting point. If you just keep it at that melting point, it'll just melt completely.
Yeah, it will melt completely. Right. Okay, so let's talk about what kind of energy is being added, because we know something's happening here. It's not temperature changes, it's something else. And that's what these questions right here are. So which segments of the graph represent phase changes? The plateaus. This is not how you spell plateaus. Is it spell plateaus? Pretty sure that's not right. But flat spots. There you go, flat spots. Okay. There we go. So those are where the phase changes are happening. Then, what is happening to the temperature while the substance is phase changing? There's no change in temperature. Okay, and my next page, I've got the other questions. This is the part we just already talked about. No, I don't have them here. We're going to go right here. Okay, so what's actually happening during the phase change? The energy added, this is the part you need to write down because you'll be expected to explain this again. Okay, the energy added to the substance is used to overcome. I'm going to put IMFs. What does IMFs mean again? Tyler? Listen, what does IMFs mean again? Morgan, IMFs. Thank you. Intermolecular forces. Okay, so the energy added to the substance is used to overcome the IMFs of the solid, liquid, and that's pretty much it because the gases are already almost all the way overcome of all of their IMFs. So the energy is not used to increase temperature. It's basically used to separate molecules. Okay, this is what it's used for. It's not used to increase the temperature. It's not really used to phase or to heat them up anymore. It's used to take particle 1 and particle 2 and move them farther apart from one another. Yeah.
What's it say after solid?
It's slash liquid. What's up? It's not used to do the temperature. It is used. It is used to separate the molecules. It's not used to increase temperature. It is used to separate molecules. That's why the temperature is not changing because the energy is used for another purpose. So that's the most important part from phase diagrams. So, not phase diagrams, heat curves. All right, so you guys have, I'm gonna let you guys practice this with a partner actually, and then we'll go to our lab. So you guys have two different versions, look right here, two different versions of this, heat curves on one side and some phase diagrams on the other. These are going to be different than what we've done in class. They'll have different identities like nitrogen or hydrogen or carbon dioxide. So make sure you read the question because it tells you some good information as you go. This is your paper, you can write on it. You probably will be able to give us your answers on here unless you write really big. So you guys can work in partner. Let's do this for like 20 minutes. What you don't finish, you will finish at home, hopefully. Alright, well, you finish as much as you can in class, okay? And pass because you got other stuff in there.
How does this stitch again?
Hmm? Yeah. Oh, I'm sorry. I got you. The ones with the... Yes. The other ones you don't know.